Differentials. What are they all about? Stick around and find out. In this video we're going to look at differentials. Now let's say for example we start off with a function here in red. Now this function here is the function y is equal to x squared, but I've only shown you it for the positive values of x. Now let's take a point along this axis, we'll call that point x. Then if we were to map that point x up through this function, we would get the point f of x. So this is the point x, and this is the point f of x. Now let's say we were to add on a small value, and we'll call that small value delta x. So this distance from here to here is delta x. So that means that the new point up here is going to be the point x plus delta x. So that's this point here. Now again, if we were to map this point here up through the function, then we're going to get a point up here, which is going to be the f of x plus delta x. So this is x plus delta x here, and this is the f of x plus delta x. Now let's say we start from this point here, and we move along the function. So the function is in red, so we're moving along the function, and we're travelling in this x direction along the function, and as we travel along the x direction, of course we're travelling up, and we're following this function up. So at some point x plus delta x, so this is a new point here, we're going to hit the function at this point here, f of x plus delta x. Now the y distance that we will have gone up as we move along this function, we're going to call that the increment. So the increment then is going to be this height here, from this point here down to this point here, because that's the distance that we have gone up as we've moved along this function, the distance of delta x. So we can see here that this value for the increment, we can call it delta y. Now this value delta y is going to be this height here, which is f of x plus delta x, minus this height here. So this height here is nothing other than the value of our f of x. So we can say that the increment delta y is equal to f of x plus delta x minus f of x. Now take your time and don't get lost in the diagram, and you can check and see that this height here is just going to be the value of f of x plus delta x, which is the full height, minus this little height here, which is our f of x. So make sure you understand that little bit. So if this distance here, delta y, is the increment, then what exactly is the differential? Well, let's talk about this first, and then we'll look at this little bit of mathematics. So put simply in words, the differential is the linear approximation of this increment delta y. Now what does that really mean? Well, let's say for example we take this point x and we find the gradient of the curve at this point x. Then the gradient is going to be given by the f derivative of x. So if we were to take that gradient and multiply it by this distance here, which is our delta x, then we're going to get this height here. Now this height here is our dy, and this is our differential. So let's take our time and make sure we understand this. We've found the gradient at this point here, and this is going to give us just this line. And we've multiplied that gradient by this distance. So we multiply the gradient by this distance, we're going to get this little height here. So in effect, this is the linear approximation of the full increment delta y. And we can see it's an approximation because we don't get the full distance delta y, we only get this small distance here, dy. So this dy is our differential. Now let's look at our differentials mathematically. We're going to start off by looking at the gradient of this function in red at this point x. You can see I've drawn the tangent at that point x, and this tangent line is in blue. So the gradient of this tangent line here is equal to the gradient of the function at this point x. Now we can see that the derivative here is going to be generated by the delta y upon delta x, and it will be the limit as delta x tends towards 0. And we can see that geometrically. If we were to draw a line from this point here up to this point here, then we can see that the gradient of this line here in black is our delta y divided by our delta x. So that's our delta y divided by delta x. But this isn't the actual gradient at this point. You can see it's out. If it was the correct gradient, then it would be lying parallel to this blue line. But if we were to allow the value delta x to tend towards 0, then the gradient of this black line would tend towards the gradient of the blue line. So let's go and do that now. We draw the line from here to here, and if we allow delta x to tend towards 0, you'll see that the black line here will tend towards the blue line. So that is the gradient of the black line will tend towards the gradient of the blue line, and in the limit the gradient of this line will be the gradient of the point x. So that's a geometrical interpretation of this simple limiting process. Now we're going to write this out in a different format. We know that if we were to join this line here to this point up here, we said that the gradient here of this black line will tend towards the gradient of the blue line as our delta x tends towards 0. Now alternatively, what we can say is that this delta y, which is this long length here, divided by the delta x, is going to tend towards f derivative of x. Now it's not going to be equal to it, but it will tend towards it. So at the moment what we can say is the delta y divided by our delta x, we can make it equal to it if we say that this gradient here is going to be the gradient of this blue line, which is our f derivative of x, but we're going to be adding on some value alpha. And you can see that we're going to add on the value alpha because this gradient here in black is steeper than the gradient in blue. So we're taking the gradient in blue, which is f derivative of x, and we're adding on an extra little bit of gradient, and that extra little bit of gradient we'll call alpha. And by adding that little extra bit of gradient alpha, we can go from the blue line here up to the black line. Now alternatively, we can take this little equation here and we can multiply both ends by our delta x. So that's going to give us this equation here, which is delta y is f derivative of x times delta x plus alpha delta x. Now this little bit of the equation has got a simple geometric interpretation. So the delta y we know is the full distance here, and it's going to be given by the linear approximation, which we've already talked about, which is the gradient at this point times our delta x, and that's going to give us our dy, which is our differential. So our differential is our linear approximation to our increment. But we're going to be left with this distance here. So this distance here is going to be given by our alpha delta x. So it means that our increment delta y is split into a linear increment here, which is our differential, and we've also got an increment here, which is our higher order values. Now, whenever we go through practical problems, what we can do is we can approximate this increment by using the differential. And the differential is just the linear approximation of this increment. Now, the idea of our differentials is best seen by example. So let's look at a simple example now, and then on the next video we'll look at a more complex example. We want to solve this problem here. We have a box which is 10 by 10 by 10, and we have the thickness of the walls which are an extra 0.05 centimetres. So that is, we've got an extra 0.05 in every direction. And we're asked what is the volume of the walls of the box. Now we can solve this again by thinking about the increment. So we can say our increment is delta y. And then we can say our increment is going to be approximately equal to our differential, which is our dy. Remember, our differential is nothing other than the linear approximation to this increment. So this linear approximation is going to be given by the derivative of a function, which is the function which gives us the volume, times the value of our delta x. So if we were to find a function that would give us the volume, well, that's simple. It's going to be x times x times x. So the function here is going to be x cubed. So we want to differentiate x cubed, and then we want to multiply it by this small distance delta x. So when we differentiate that, it's going to give us 3x squared times delta x. So we're going to have our 3. Our x here is our 10. So it's going to be 10 squared times this distance delta x. Well, the distance delta x is going to be 0.05 in one direction and 0.05 at this direction here as well. So if we add both of those up, we'll get 0.1. So that's going to be 3 times 10 squared times 0.1, which is equal to 30 centimetres squared. So you can see here in this particular example that we've used the differential in order to find out the solution to this problem. But we've only needed to use this one term here, which is our differential. You'll notice here that in this instance, this extra term here is actually equal to 0. Now the reason for this is that in this particular example, it's quite a simple example, meaning that if we were to increase the thickness of the walls, then the volume would just increase linearly with the thickness. So that would mean, for example, if we were to compare it to what we've seen before, in effect, instead of having a function which would be a curve like this, our function would actually be a straight line. So if our function is actually a linear function, that would mean that our increment here would be the same as our differential. And that's what we've got in this particular example. But what we're going to do is we'll move on to another example. In this other example, you'll see how we're able to split up the increment into the differential and also the higher order terms as well. So we'll get to that in the next video. Now there's one other important thing we want to cover before we finish. We talked about the differential here, dy is equaling the f derivative of x times the delta x. Now the dy has a finite magnitude and the delta x is a finite magnitude. Now we can replace this delta x here with the dx below if we say the dx here, like the dy, is a finite magnitude. So we can rewrite this as dy by dx is equal to f derivative of x, and this is our common way of writing our differentiation. So now when we think about it in terms of differentials, we think about dy as having a small but finite magnitude and our dx as having a small and finite magnitude. So this means that we no longer have to think about dy and dx as being infinitesimals, we can actually think about them in terms of the differentials. And this is important because it banishes the idea of infinitesimals and it replaces them with the idea of differentials. And the idea of differentials can be defined in terms of finite magnitudes. Now notice also we can actually make the difference between our delta y and our dy as small as we want, and we can make it arbitrarily small by making the value of our delta x arbitrarily small. Now these ideas have got a bit more meat to them, and we'll talk about them in a different video when we cover the idea of epsilon and delta. But let's go ahead in the next video and we'll look at the other example which gives us a change which isn't a simple linear change that we see in this example here. Thank you for listening. I'll get you on the next video. Goodbye.